I will be talking about the change to SELinux today. I will give you a short introduction, then I will tell you how SELinux works, at least on a really basic level. Then I will tell you about our motivation for the change, and then I will explain to you what this means for you. And maybe a short heads up, because I already met someone that was at SUSECon last year. If you've been to my talk there, then this one is going to be really, really similar. The only additional change here is that I will show you some confinement change at the end, where I will go into an SLES domain and will show you how it makes my life harder as an attacker. Good. So my name is Johannes Segitz. I'm a security engineer working at SUSE. I live in Germany, Nuremberg. And I do a bit of code review, not that much nowadays because I kind of lack the time to really look into code for hours on end. I do product pen testing, so before you get a SUSE product, I will have a look at the product from an offensive point of view and we'll try to figure out if there are any security issues that we did not see. I'm an SLES expert and I'm the lead of the engineering red team. So we do regular red team exercises within the company where we try to figure out ways how to attack the company from the inside. And yeah, that's a lot of fun. And also great to be in Florida. It was my first tornado ever. So I don't know if you already been here yesterday. That was kind of fun. I mean, did not really see here anything, but it was enough to spook out my whole family. Good. So a little bit about the SUSE product security team. First of all, there are many security teams by now within SUSE because we've grown so much. So we are the product security team. There's a cyber security team. We have a certifications team that is for security certifications. We are split up into groups. We have a reactive group here, and they mainly do classical incident handling. So security issue is identified, it gets a CVE, we analyze the security issue, we check where are we affected, how does it need to be fixed, and then we make sure that this is delivered in the end to the customer. We not only do that for SUSE, but we also do it for OpenSUSE, which greatly extends our scope, because OpenSUSE has, I don't know how many packages, but more than 10,000 packages. And that causes us to really go over a lot of security issues every day. And then the proactive security group, where I'm the lead, there we do all of the security work that we do before shipment. So code reviews, also hardening. Of course, there are certain limits, because if we would harden the product as much as we personally would like, then most customers would hate that because it's still a general purpose operating system. So it's tricky to find a good balance here between finding meaningful security hardenings, but then again, making life not too hard for people. And it's mostly a fun place to work unless someone discovers a major security vulnerability just before a holiday. So you all probably have heard of the XZ vulnerability. And getting that right before Easter, that is very annoying. So if you ever find a security vulnerability, please tell us on a Monday. So we have to full work 2 weeks on this.
So if I really want to screw you, I do it on Friday, nearly end of day.
Yeah. Exactly. So don't do it.
Okay.
Or alternatively, okay, maybe now put it a bit lower again.
There you go.
Better?
Yep.
Okay. The other thing that can really screw us over is the kernel team deciding to issue CVEs for pretty much everything under the sun. And I personally don't disagree with them. I think it is good that we have the tracking now, but obviously it is kind of a pain for us if we have to go over all of them and they just push out 800 of them on a day. So let's go into SELinux and maybe cover the basics a little bit. So before we talk about SELinux, let's talk about discretionary access control. This is the usual form of access control that we have in Linux and that you're probably all familiar with. So we have a typical example here. We see the etc shadow file here, and we see it belongs to the user root, to the group shadow, and it has certain access rights that are assigned to the file. The discretionary part here is the fact that the owner of an object can control the access to the object that they own. And that might seem very natural to you, but that is not necessarily the case in an access control system. It is very convenient that you're able to do access control that way, but it also has a couple of drawbacks. The drawbacks here are, first of all, it's because, so you only have these 3 access bits, and yes, there's a little bit more. You can work with access control lists, and there are setuid bits and whatever, but in the end, that is basically what most people use. It's also prone to user error, so nothing on your system will prevent something like that. If you want to make your private SSH key read and writable by everyone else on the system, you can do that. Then your SSH client will complain about this, rightly so, but that's like one of the cases where you might notice that. In a lot of cases, you will never notice something like that. It's also pretty hard to analyze, because the information you need to analyze the security of the system is spread over the whole system. So first, you would need to walk the whole system to get all of these access rights. And once you have them, you can't be sure that it's still the state that the system is currently operating in, because someone else might have changed their their privileges already, or changed access permissions to something, and you might not notice that. Also, the fact that you have the root user, who's basically godlike on Unix systems, and we try to get around with that with capabilities and stuff like that, but in the end, half of the capabilities are basically full root anyway, and the other part is not that useful. So it is a good system in general, but it definitely has some drawbacks. So let's talk about mandatory access control. And the operating word here obviously is mandatory. So that means in this context that the access control decisions are not made by the owner, but you have a centrally managed policy that defines which kind of access is allowed on a system. And that has a couple of advantages. So first of all, you can put access control in the hands of experts. You can obviously also just let everyone decide what they want to do here, but I would highly recommend using experts here. And that also means you can easily control the policy, because you have one policy that is loaded at a given time, and unless this policy is changed, you know that your system was in this state 5 minutes ago, and it will be in 5 minutes' time. There's just no doubt about this. And you can also do very fine-grained access control if you like to. You can do things like compartmentalization, where you say, this part of the room has top secret clearance and has a need to know for a certain operation, but other people don't, and you can easily do that with SLENOX or with mandatory access control. It also has a couple of drawbacks. So first of all, it's harder to understand, and some of you might appreciate after the talk why it's harder to understand, but if you ever got in touch with SLENOX before, you probably experienced that yourself. It can be more complex to administrate. I mean, first of all, you have this additional level that you need to take care of, so that is by definition more complex. But it's also something where a lot of people just don't have a lot of experience, and that then makes it really tricky for them to understand the basic concepts behind SLENOX. So, why do we use it then? In general, it really increases the security of your system significantly. We have kind of a birth defect in operating systems that quite often processes have a lot more privileges than they need. If you look at a modern operating system like Android, for example, they went with a completely different design. So no one would design an operating system the way that we have them nowadays. But we are stuck with this system, and so we need to try to tack on security later on, and that means we need to confine processes to the least privileges that they need, and SLENOX is really good in that. So the basic idea of SLENOX is type enforcement. And that means that every object on your system has a user, a role, a type, a sensitivity, and a category assigned. And if you put this all together, then this forms the so-called security context. So this long string here is a security context. You don't necessarily have all of the different fields here. Sometimes like the last part is missing. But the good news is that most of the time you can ignore everything but the type and just concentrate on these types, because they are the most important part within SLENOX. The other parts can also bite you, but the first problems you will have will definitely be with types. Pretty much everything on a system has a security context. So sockets, packets, there are over 130 different security classes. Obviously, all of the easy, normal objects that you know have them too, and you see them if you add a capital Z to most commands. So if you list a file and add a capital Z here, then you see that the etc shadow file has this security context. And again, you can ignore pretty much everything apart from the type. The type is shadow T. And that's already one lesson, so quite often you have a pretty good correspondence between the object that you're looking at and the type that is used for that. So that the shadow file has the type shadow T, kind of makes sense. If you see something different here, then this is probably something you want to fix. Yes?
I also want to point out one thing that I didn't know until a few weeks ago, but it's super good to know. When you do ls, even without capital Z, that dot that shows up at the very end of that DAC list of conditions indicates that there is a security context applied to the file. So if you're looking at something and it looks weird and it says the permissions is normal, you see that dot, that means that there's a security label applied to it. You can do -C and then see what the label actually is.
That is a very good note. It's always good to have Neil in the talks. Good. Similarly for processes, again, you add a capital Z, and here just grabbed for the postfix master process, and there we see the security context, and the type is postfix master T, so that seems to fit. Not every of these rules are applied by the kernel. There are some user space enforcers, like systemd is a great offender, databases, windowing systems, so you can really control a lot of accesses within your system with SLENux. 99% will be within the kernel, but there are also other components that play into this. The basic idea is that first you have DAC, so the normal access control. That means if you as a user, for example, try to read etc shadow, you will not see an SLENux denial for that, because DAC will already prevent you from doing that, at least I hope on your systems. Then you have SLENux, which is a deny by default system, so it's similar to a well-configured firewall. You need to allow everything that you actually want to allow, everything else is denied. And thinking of it as a firewall for system calls is also a very good way of thinking about this, because it is really good correspondence quite often between the sys calls that you see in a workload and the permissions that you need to give a certain process. So if your process wants to read something, it will probably need a read permission, and quite often you have this one-to-one correspondence. You see here we have a subject trying to access an object, you have certain operations, and then you have one security context doing operation on a different security context, and that's the way how you think about SLENux. And the good thing again, ignore everything apart from the type. Everything else for now is a bit confusing. There's one specialty where you might run into this in the beginning also. This here are the categories, and this is used to separate containers and virtual machines from each other. Because they have one type, container T for containers, but you obviously don't want container A to access container B. And so SLENux uses the categories to separate these. This is the one thing that you should know in the beginning, apart from the types. So we always supported SLENux. So we had the tool chain, but what we did not deliver was the policy, and that's like the big thing. We will now deliver the policies from SLE 16 and up, and SLE Micro already has it enforcing. And they come in 3 different flavors. So it's the so-called minimum policy, which only confines a certain set of daemons. Then there's the targeted policy, which is the default policy that we ship that contains pretty much everything in the system. And then there's the MLS system, which stands for multi-level security. And this, I don't even know if we ship that, but you should probably not use that because that is definitely not ready from our side. It's also not relevant for most people. So unless you're military or like Secret Service or anything like that, then you probably will not need this, and it's also pretty complex to do. An SLENux policy consists out of different modules that you can dynamically load and unload. The current policy that we ship has around 440 modules that you can load. And if you want to write a policy module, then you have several ways to do that. And I expect that in most cases you will not really need to do this, but I want to quickly at least show you how this would look like so that the first time you get in touch with something like that, you don't freak out. So let me quickly show you an example of an SLENux policy module. AppWatch is a tool that allows you to sniff the network and see if someone is attacking you on the network via certain network attacks. And this is a pretty common pattern that you see quite often. So you have a type that is actually used for the running process. And then you have an executable type that will be used for the executable binaries on disk. And then you tell the system, if the init domain executes these executables, then transition into this type. So this is a really standard way of doing things within SLEnux. You usually also want to make sure that you have your file type separated. So for example, in this case here, we have AppWatch data T. So the AppWatch daemon has certain data files that it wants to use. So we separate this out so we can strictly control access to that. But we also need to interoperate with the rest of the system. And for this, you have something like file type, which is an interface that you can use within the policy to inform the system, I will use this type for files. This allows then applications like, for example, a backup software to request the permission to read all files. Because if I would just define this type and use it privately within my module, since SLEnux is a deny by default system, then other parts of the system would not be able to read this. You also need to initially label your system, to do this initial labeling of your system to make sure that everything has the proper type from the beginning. You have files that define via regular expressions how the system should be labeled. So here we see just a plain path. The AppWatch binary will receive the type AppWatch exec_t. The data files that we just discussed are under var AppWatch, and then you have a regular expression here that defines that everything below that path will be labeled this way. The important thing to understand is that these labeling rules will only be applied once when you label the system. You can, of course, always request a relabel of the system, but after that, the system needs to stay in a consistent state. And one of the really common problems is that if people are not SLEnux aware and just copy around files without understanding what they are doing, then they might get the wrong type, and then the system starts to break down. So if you have really strange problems, relabeling the system under SLEnux usually is the equivalent to rebooting in Windows, so it's mostly a good idea.
And you don't have to restart.
You don't have to restart, yeah. Depends on how massively you screwed up, but yeah.
Most cases you don't have to.
So these are the SLEnux denials that you will for sure see sooner or later if you work with SLEnux. I broke it up here a little bit because usually it's just one long line. Type ABC, this tells you this is an SLEnux denial. You see something was denied, something tried to transition, then you see a bit of the binaries that were involved. So we had something with the SSH daemon and some shell. And then we have a source context and a target context. And here you see two security contexts again. And again, you can ignore everything apart from the type. So we see kernel T tried to transition to unconfined T. And that might seem reasonable, but if you have worked with SLEnux for a while, then it's a pretty clear indication that something was mislabeled on your system. So relabeling the system will likely fix a problem like that. The good thing is there's also tooling that helps you with that. So there's a daemon that scans for these denials, and it will then suggest you several ways how to deal with that. Mostly it's pretty good, but you should not blindly trust it. So let's say you have a denial. The first thing you should always do is consider what you're doing. SLEnux is a security system, and yes, sometimes something is wrongly configured, but sometimes if your security system tells you stop doing that, then you're probably doing the wrong thing. That's not always the case, but you definitely should not have the mindset of, well, I just need to get this working. You need to understand why did SLEnux try to deny that. Then what is really often the case is you just have your files in a different location. So let's say you're running a web server application and files are on a non-default location, then SLEnux probably does not understand that the web server is allowed to access these files. So you need to create labeling rules to properly label these files, and then it will work. Then you can use tools like audit to allow, which is a really nice tool. It takes these denial messages, and it will then spit you out rules that would be necessary to actually allow what you're seeing there. But you should only do that if you're really confident in what you're doing here. Because if you just allow everything that you see, then you can also just take a tank instead of a car and just go over the whole city instead of using streets. I mean, it works, but it's probably not the right thing to do. And if everything fails, then you can still set either the system or a certain domain to permissive. So you can set the whole system to permissive. That means that you will still see the SLENOX denials, but they will not prevent anything. You can also do that in a more fine-grained way. So for example, you can say for the web server domain, only this domain is permissive. Everything else will still be protected. No? And I think we talked about this just before. So this is actually a command to do this for, in this case, OpenVPN, if you run into problems there. This is definitely the better way to deal with that, because quite often people just disable SLENOX completely, and from a security point of view, that's a really bad idea. And if nothing of these ideas here really help, then just open a bug and we will then figure it out. So, audit to allow, we already briefly covered it. It analyzes these SLENOX denial messages. The good thing about it is it's pretty smart. So it understands policy interfaces, so it will not just give you the raw rules, but it will give you the right function calls, so to say. And there's also a concept of booleans within SLENOX. These are small toggles that allow you to modify your system. And a good example is, again, a web server. There are, for example, universities which allow users to have a certain directory in their home directory. And if you put HTML files or whatever in there, then it will be served out via a web server. That is a nice system, but it also requires the web server to be able to go into a home directory. And in most systems, you don't want the web server to be able to access home files. Yeah? So this is something where you need a way to toggle it, and these booleans are a way to quickly change the system in a certain way. And audit to allow is smart enough to understand that if you feed it some denial, that would be solved by setting one of these toggles. It will tell you that, so that is pretty convenient. And yes, it is very, very helpful, but please really understand your problem first. I've seen people doing something like having a loop that constantly just scans the logs and feeds everything into audit to allow, and then allows everything that they see as a denial. I mean, yes, that works, but you would not do something like that with your antivirus or your firewall, so you probably also don't want to do that with SLENOX. So let's quickly talk about the motivation now that I told you about all of the things, how it can go wrong. Why do we change from AppArmor? We had AppArmor first, and now we switched to SLENOX. Both systems are really good mandatory access control systems. It's not that AppArmor is bad and therefore we decided to go away. It's just that SLENOX has seen a lot more traction over the last couple of years and is, for example, the default Mac system within Android. So upstream is pretty active. In general, we just see a lot more activity on the SLENOX side. And especially if you're in a high security environment, then SLENOX just offers more. You can do mostly the same things with both systems until you get to a certain stage where with AppArmor it becomes really difficult or next to impossible to do something, and with SLENOX it's still possible. And also the policy that we ship has a lot better coverage. So for previous SLES releases, we mostly concentrated on the networking facing daemons because they are obviously the biggest attack surface. With this SLENOX policy that we now ship, it really has policy modules for pretty much everything on your system. So not only the network-facing daemons are protected, but pretty much everything that runs on your system will be in its own SLENOX domain and confined. So what will it mean concretely for you in your workplace? The important thing is, no matter what, you will need some basic SLENOX knowledge. And if you are in a team of IT professionals, then probably everyone needs to have at least a basic understanding of SLENOX. Not everyone needs to be an expert here. It is sufficient if you have one that is able to debug something there, but they need to understand that SLENOX exists and that it can cause problems. Because otherwise you have an operation that used to work, suddenly it doesn't anymore and people don't know where to look. So this magic capital Z flag is like magic. You need to know that you need to check for something like that. So what it also then depends on is your current situation. Let's say you're a plain user of the default system. You have the existing AppArmor profiles. You did not develop some of your own. Then the change is probably going to be really easy for you because you can probably just migrate from SLES 15 to 16 because you don't have any special needs there. You get a much broader protection with the SELinux policy for basically free. If you have customized AppArmor profiles, then it becomes a bit more difficult. So the easy case for you is if you added some AppArmor profile for something that did not exist before, and now there's already an SLENUX policy module for that, then you can likely just take the SLENUX policy module and get equal or maybe even better protection. If not, and if you want to keep that, then you might want to write an SLENUX module for your workload, but that's really more of an advanced topic. It's unfortunately not that easy to write really good SLENUX policy modules. You might want to consider containerizing your workload, because we will talk about this on the next slide. Because if you containerize your workload, then you will likely already get SLENUX protection via the container, and you don't have to figure out a good profile just for your workload. So if you disabled AppArmor until now, then please don't tell me I'm a security guy. Just act your way like like this is not the case. And in general, I would really recommend not doing this. I know that these systems can be painful at times, but they're really worth it, and I will quickly show you once I'm done with my talk here. And if you already containerized your workloads, then you probably have a pretty easy life. There are some generic policy modules that cover containers. Of course, you can always get more specific, but even the default policy modules for containers already provide really good protection. So unless you have special requirements, then with a containerized workload, you're probably already good. Good. And I will now show you a small confinement demo. And because I'm brave, I did not record anything, and it's a live demo. So let's see. Good. What you see here on the left side, and I hope it's readable, but I think it is. I just had an eye operation. I can read it, so if you can't read it, then you probably also need an eye operation. What I will do here first, I will first set the system in permissive mode, so allow everything on the system. And I just told you don't do this, and this is just a play system, so please don't do this. But the problem with SLENUX is that quite often it's so tight that for debugging or showing certain security vulnerabilities, I need to go into permissive mode. Otherwise, I would not be able to do what I want to do here. This run
You're trying to do a bad thing. So.
Yeah, exactly. I will try to run this shell, which is a Metasploit shell that allows me to then connect to a system to emulate an attacker that was able to breach into the system. And in this case, I emulate ChronyD, which is a timekeeping daemon. So it emulates an exploit that allows me via the network to get onto the system and act as this timekeeping daemon. On the left side, on the right side, we have the SLENUX denials of the system. At the moment, nothing is shown here. And now I started this, and you see the first SLENUX denials. These two would prevent me from running the demo. That's the reason why I needed to first go into permissive mode. And now I will do it backwards. So I will go into enforcing mode again to actually show you the problem. And then I will connect to the system. So what the binary that just spawned did was open a reverse shell or a bind shell on port 8888. And I will now connect to this. And this is a pretty standard attacker workload. You usually have a bit of more advanced command and control network and everything. But yeah, we just want to keep it easy. So now I'm here on the system. And let's say I want to check my credentials first. So I type ID. See that I'm running as root. And I'm running as this security context. So as I intended, I run as this crony domain. No? And let's say I want to do some standard operations. So let's just look in the system, check what is running. And when I do this, then you will notice two things. First of all, this wall of text here. And also that apparently there's not much running on the system. And the reason is that this cronny domain is not able to see all of the other processes that are running because it does not have the necessary permissions. That's also why we see these many, many denials that just popped up here. And this is the thing that is really annoying as an attacker. First of all, you become extremely noisy because everything that you do might result in a lot of denials. I just checked the process list of the system, but since I was not able or not allowed to get the information of all of these different processes, every time I try something like that, I will generate a denial. And this is really, really good information if you want to protect your systems. Once you have a good baseline and see that some system is freaking out and spewing a lot of these AVCs, that is a pretty good indicator of a compromise here. It also just shows that I can't see a lot on the system. So let's say, I'm root, so I can definitely just go into the home directories and list these. Well, I can't. Because this timekeeping daemon has no need to actually go into the home directory. So as an attacker, I also can't do the same. Similarly, for the root directory, even though a root, I can't open it. And let's just say I want to add some backdoor to come back to the system later on. One easy way would be to add a new user account. I would add proper information in here if I would be a real attacker into the passwd file. And again, I'm not allowed to. No? And this should just serve as a motivation to make sure that if you have the chance, don't disable SLENux. It is really, really helping. There are some exploits that don't work anymore, but it's also this part here. It makes you very, very noisy. And if you put good monitoring onto these denials, then you can catch attackers before they can cause any additional harm. Good. I'm happy that it worked.